webinar at the end of this session. And we're generally following a monthly webinar schedule. Next slide. Next slide, please. Okay, some housekeeping items before we get started. Just to familiarize yourself with the go-to screen, there's an attendee control panel where you can go for the audio on the webinar. You can use the audio through your computer or your phone. You can consult the directions in the audio pane on how to do that. At any time during the presentation, you can type questions you might want to ask the speaker in the questions pane on the side. And as a moderator during the Q&A time, I can read the questions out for the presenter so that everyone can hear the questions as well as participants. Also, I want to note that I want to make sure that everyone tries to mute their phones to cut out background noises and distractions. This webinar is being recorded, so you receive a link to the recording after the webinar. We also ask to take a moment to complete the evaluation survey that pops up at the end of the webinar. This will help us with future events and future webinars. If you'd like a copy of today's slide, please find a PDF of the handouts in the handout section on the control pane. And if you're really into technical issues and tech savvy, you may want to tweet about today's webinar by using hashtag SWSwebinar. Slide, please. So with that, let's start our webinar. And we've got Gail Shimura. Dr. Gail Shimura is an Associate Professor of Geography Department at McGill University, past Director of Quebec's Global Environment and Climate Change Center, and past President of the Atlantic Canada Coastal and Estuarine Science Society. She's conducted research on tidal wetlands along both the Atlantic and Pacific, and over a wide range of latitudes from Hudson Bay all the way to the Gulf of Mexico. Recently, she was the lead author on Coastal Wetlands chapter on the Intergovernmental Panel on Climate Change Publications for guidelines to national greenhouse gas inventories, the wetlands section. Dr. Shimura has also used technologies of paleoecology, modern ecology, and geomorphology to study tide marsh response to sea level changes, impacts to climate change, and human perturbations of coastal ecosystems, and ecosystem services of natural and recovering salt marshes. Presently, Gail's lab research is largely focused on the impact of nutrient pollution on coastal ecosystems, assessment of soil carbon stocks and the rates, and greenhouse gases fluxes in marshes. So with that, Gail, I will turn it over to you.
Thank you, Jeff. And I'd like to thank the Society of Wetland Scientists for giving me this opportunity. And I'm hoping the slides advance because I don't have any advance yet. Oh, here we are. Okay, thank you. Yes, I'm talking about climate change and blue carbon, and specifically the topics that you see listed here. Starting with what is blue carbon and ending with how we can think about mitigation in all different ways in relation to blue carbon. So blue carbon, what is it? It's the carbon stored in vegetated coastal ecosystems. And by vegetated, I mean emergent plants, higher plants, like you see here in this tidal marsh. It's also the carbon stored in mangrove swamps. And if you're not familiar with the distribution of mangroves and tidal marshes, they both will grow in protected embayments, coastlines that aren't exposed to the full brunt of the ocean. So these geomorphologically, they fill similar roles, but we find tidal marshes most prevalent in temperate to Arctic climates, and mangroves as the tropical cousins, if you will, from the warm subtropics through tropical lands. What's important about both is that they accumulate carbon in their soil. I'm sure a number of you will immediately note that mangrove wood stores a substantial amount of organic carbon. But trees die. In many places they're still harvested, and above ground wood will decay. So it's the soil that's stored, the carbon that's stored in the soil, that is really the protected and important blue carbon resource. In addition to tidal salt marshes and mangrove swamps, there's blue carbon stored in the soil, the sediment, the substrate. I'll use these terms interchangeably, in seagrass meadows. And the difference with seagrass meadows is that these are not intratidal, but generally subtidal. And they're not as often referred to as having soil, but in the U.S. they actually are recognized by the Soil Conservation Service now as a type of soil. Okay, so this is what it is. Why is it important? Soil stored in many ecosystems, and it has carbon. So why is blue carbon so important? So if we take a walk through creeks at low tide on the Bay of Fundy, we have a great opportunity to view a blue carbon deposit, or peat, or sediment, or soil. And that's what you see in this photo. You see the creek bank exposed at Dipper Harbor on the coast of New Brunswick, where the tidal amplitude is 6 meters. That's the low tidal amplitude here in the Bay of Fundy, because it can reach even 11 meters. So at low tide, the water's completely gone from the creek. We can walk through the creek, and we see 3 meters of marsh, and you can even see the rhythmites, which represent, going back and forth, these horizontal lines. Those represent tidal deposits, because the marsh has built up over the last 3,000 years as marsh grasses colonize the sediment. Their roots and rhizomes extending into the sediment increase the volume, and by increasing the volume they essentially increase the elevation. So as sea level slowly rose over the last 3,000 years, the elevation of the marsh also rises. Now, if there is suspended sediment around in the tidal floodwaters, that also gets deposited and can add to the elevation. But most of us consider it is the organic material, the vegetation, that is the big driver of the elevation change, and has enabled marshes and mangroves through the same process to continue to accrete over time. In fact, let's see if I can advance. Yes, there's a lag on my side. I'm not sure on the audience's side. So these processes have allowed mangroves and salt marshes to accrete as sea level rose, in fact, over the Holocene. This diagram was prepared by Bloom in 1967, and it shows time in thousands of years from 10,000 years ago to approximately today, and depth in meters from the surface to 13 meters. And since 1967, salt marsh and mangrove deposits have been used as records of relative sea level rise. So for the duration of the Holocene, since the end of the last ice age. And Bloom was comparing rates of rise at Barnstable Marsh, Massachusetts, all the way to the Everglades in Florida. And I just showed you a site in Canada which has been dated to 3,000 years. So we have these deposits accumulating over thousands of years and still recognizable over thousands of years. So we have great evidence of the long-term carbon sink. So we have these stocks, but what's also very important is the rates, the modern rates of soil carbon accumulation. This graph shows carbon burial rates in grams of carbon per meter square per year, and note it's a log scale from 1 to 1,000. And what we're comparing is average global rates, salt marshes, mangroves, and seagrasses to terrestrial soils. And what we see is that salt marshes and mangroves in particular have substantially higher rates of soil carbon accumulation than we find in boreal forests, where we don't expect to find much carbon in the soil, or temperate forests, tropical forests, where we don't expect to find much, temperate forests, and boreal forests, where actually we do expect to find some organic matter accumulating. But they are substantial, have substantial rates per unit area. So, as a reminder, they're storing it for millennia. You're viewing 3,000 years of carbon accumulation in this one marsh. However, if you study freshwater wetlands, particularly bogs and fens, or have read about them, you realize that they also have been accumulating carbon for thousands of years. So why are we distinguishing blue carbon? Well, one, they don't saturate, but neither do freshwater wetlands. By saturation, I mean that terrestrial soils have a balance between the amount of carbon that can be fixed and the carbon that's decomposed. As an example, if you agricultural soils can be managed to increase the carbon storage capacity, but there is a maximum that's usually reached after about 50 years, and then there's an equilibrium between the carbon in and the carbon out. That doesn't happen with wetland soils because they're saturated and they can keep accumulating, and the deposit can get thicker and thicker. The difference between freshwater wetlands and salt marshes and mangroves are that the latter do not emit other greenhouse gases besides carbon dioxide, which of course comes from any organism that's respiring. If pollution levels are low and salinity is high, about 18 practical salinity units, then we see no nitrous oxide coming from the soils and negligible emissions of methane. Yet many freshwater wetlands are notorious for releasing methane from their soils. And this is important not just because it's a loss of carbon, but over a 20-year time span, methane is 86 times more powerful a greenhouse gas than carbon dioxide. Some of you might have heard Scott Neubauer's webinar. I believe it was last fall. And he and Pat McGonigal have developed a metric to be able to determine what is the climate feedback when these gases are released from wetlands, or when, in the case of salt marshes, they actually act as a sink. Some measurements in salt marshes have shown them to actually be sinks for methane rather than releasing methane. So it makes the carbon stored in salt marshes and mangroves all the more valuable, hence now branded. Some of my colleagues say, blue carbon, why do you have to have such a focus on this? We're ignoring all the other ecosystem services. Indeed, salt marshes and mangroves do provide a number of really important and valuable ecosystem services. Not in terms of plant diversity. They're notoriously low in plant diversity, but they do both support global biodiversity. Here's just one example, and this is something my lab has studied. The maritime ringlet butterfly, which you see in the lower left, spends its entire life cycle in salt marshes. The entire population of the maritime ringlet butterfly lives in only a handful of salt marshes on Chaleur Bay on the coast of eastern Canada. That's it in the world. And there are a number of other examples that I could give you, but that's the topic for another talk. Of course, plants in marshes and mangroves can be harvested. Produce markets in Europe and even in Quebec, where I live, sell salicornia, a plant native to salt marshes. But what they're more recognized for is the secondary production, the support of waterfowl and in particular fisheries in the waters off the marshes and mangroves. So commercial fisheries and shrimp fisheries in particular have been shown to benefit from greater area of mangroves in coastlines. The local public would probably more readily recognize the value as a means to mitigate storm energy, wave energy, when it hits the coastline. And we have some rather tragic evidence of the value of mangroves when we look at shorelines in the South Pacific that get hit with the big tsunamis and see that where there are mangroves, there was greater protection. So yes, we have these. But what I maintain is that without sustaining the carbon sink, we cannot sustain the ecosystem, because the processes that sustain carbon sequestration are essential to the sustainability of a marsh or mangrove system. Without carbon sequestration, there would be no substrate sustained, and there would be no salt marsh or mangrove. In fact, there are some mangrove and salt marsh soils that are totally organic. They'd be classified as histosols in the U.S. system. Okay, so now we move on to, well, who cares? Well, you know I do. As wetland scientists, we all care about wetlands because we recognize that they provide valuable ecosystem services, or as a wetland manager, or if you're just a wetland enthusiast. However, the climate mitigation potential of blue carbon sinks has driven the interest internationally. In 2003, the first empirically based estimate of carbon held in salt marsh and mangroves deposits was published. In 2009, international NGOs decided to brand it blue carbon and use it as a tool for conservation of these habitats and bring it to the attention of the COP at International Climate Negotiations in Copenhagen. Now, there were two documents prepared. One was by the IUCN, notice the Management of Natural Coastal Carbon Sinks. The authors, and I was one who contributed to this, said, blue carbon, what a silly name. No, we will not publish under that. The United Nations Environment Program prepared a parallel document with a slightly different focus, but used the moniker blue carbon. And I have learned my lesson of the importance of branding, because now we find blue carbon all over the map. There are blue carbon projects funded in the Mideast, locally. There are African projects. There are regional, national, international working groups. It's regularly brought up to the COPs. For instance, this open statement to delegates of COP 16 by the Blue Climate Coalition. So there's a coalition, international working groups. I think I mentioned that there were the national and regional. There's the U.S. government is interested in blue carbon. The agencies are looking at blue carbon, and blue carbon was even noted in an executive order of the Obama White House. There's the blue carbon community, and you could visit their blue carbon portal to get more information. Or as Arlo Guthrie would say, it's a movement. I'm not sure if we have a song, though. I apologize to the millennials who may not appreciate that joke. So, what might happen to blue carbon with warming climate and the other things associated with climate warming? That's the next topic. In terrestrial ecosystems, we most often think about species range shifts. That's the common thing that's thought about. So I'll start with that. I probably do not have to remind you that carbon dioxide has been increasing in the atmosphere over the last century. This black line represents carbon dioxide increase. This right-hand axis represents carbon dioxide concentration in the atmosphere, parts per million. The bars represent global average temperature from a baseline, diversions below and above that baseline, and it's in degrees Fahrenheit. I apologize. I really like this diagram, and I can't find one with centigrade that shows it. No matter what goes on in the media and what governments say, we still keep seeing an increase. In fact, in 2015, the Mauna Loa Observatory recorded an average of 400.8 parts per million carbon dioxide in the atmosphere. So we're off the graph. We have to rejig all these graphs now. And of course, with rising carbon dioxide concentration, we have increased temperature. The major greenhouse gas is carbon dioxide because it's such a great volume in the atmosphere, and we're actually not bringing it down. So, as I mentioned, terrestrial ecologists have been noticing and are very concerned with range shifts. And one of the many examples is the sooty Cooper butterfly. And I'm not sure why I chose this because it's difficult for me to say, but maybe because it had these nice clear maps showing retractions in red, expansions poleward in green, and then in blue the maintained range of it. So we can expect loss and advances of ranges, at least in terrestrial systems. That's what they've shown. And this is in Europe, where climate has warmed by 0.8 degrees C over the last century. The situation for intertidal organisms, however, is more complex, which is maybe why we don't have so many examples. Excuse me. Both flora and fauna of salt marshes and mangroves will be affected by not just changes in air temperature, but also sea temperatures. And here you're looking at the average February temperature today in the sea surface, and the average August temperature, which we often use to represent winter lows and summer highs. Now, besides sea and air, for fauna, we have to consider the sensitivity of multiple life stages that can range from planktonic to sessile for a single species. So, even more complicated. What I'm going to look at are just two locations where I think we're observing range shifts in coastal species that could affect blue carbon. Here at Cape Cod for summer, and the northern Gulf of Mexico and coast on the left coast of Atlantic coast of Florida for summer. Let's start with the northern one. Okay. Now, fiddler crabs, which are shown on the photo on the right, are easily recognized. You've probably all seen something on TV somewhere with these males waving their big claw around, which is pretty useless except for waving it around. When they're not waving their claw, they join the females in more constructive activities, eating and, very important, burrowing into the marsh soil. You can see not much vegetation where these are. The northern limit of fiddler crabs, Euca pugnax, is just north of Cape Cod. Here is Cape Cod on the map on the left. If you're not familiar with this region, it's just south of Boston, and New York City is down here, out off this graph. And this is the northern limit of fiddler crabs. These diagrams here represent results of genetic research that Sanford and others produce to look at how species may actually expand ranges by having some genetic shifts. But what was more interesting in the study by Sanford and others is the fact that they took adult fiddler crabs and put them far north outside their range, somewhere up here. I didn't get a chance to figure out exactly where, but in places where they experienced much colder winter temperatures, the adults survived. So it's not the winter cold that limits fiddler crab expansion. What it is it's the summer water temperatures that limit their expansion, because the pelagic crab larvae, which are released in somewhere mid-June or July, require a certain number of days at a minimum water temperature. And without that enough heat, they don't develop, they don't mature, and they don't then colonize an area as adults. So we see them limited to here. Now, with water temperatures and climate warming, Johnson thinks we're seeing an expansion of the poleward edge or the northern edge of the range. And in 2014, he reported that they're now seen in New Hampshire, which is unfortunately off this map. It's right about up here. And he thinks that's a valid range extension, not just a temporary excursion, which happens with particularly marine organisms that can, in a couple good years, suddenly float into a place, but then not survive. So Johnson thinks that this fiddler crab is expanding its range at 7.2 kilometers per year. What does that mean to blue carbon? Well, we have to go south to figure that out. And we go south to a study by Thomas and Bloom back in 2010, who looked at marshes that had fiddler crabs and some didn't. They don't, even we're in the middle of their range, you don't necessarily see them in every single marsh. And they compared root production, decay, and looked at organic matter accumulation rates in these two kinds of marshes. Here you see in this table grams of carbon per square meter per year of organic accumulation. So I've looked at natural fiddler crab holes, and in marshes without fiddler crabs, they put in holes. So they have artificial holes and natural holes. And what we see in both situations is rather than carbon accumulating, we see a deficit of carbon accumulation. So it means that, and that's probably through aerobic respiration of microbes, because that makes for faster decomposition. So it may be that northern marshes could lose some of their carbon stock. But wait, there's more, and we'll get to it later in terms of what could happen to these northern marshes. Okay, so now we're heading to equatorwood, where the increase in winter temperature may make a difference. And here you see projections of two global climate models, the Hadley model and Canada's global climate model, for average February sea surface temperatures for the most dramatic scenario that's now used, and that's the reconstructed concentration pathway, RCP, of 8.5, meaning 8.5 watts per meter square per year. And again, red means warm, deep blue means colder. And even though models have different results, for this region, they seem pretty consistent. So what's happening down there? Whoops. Let me go back one. Okay. In this area, we're at the poleward limit of mangroves. Mangroves are limited by winter cold and frost on the Atlantic coast of Florida and across the northern Gulf of Mexico. The black mangrove can withstand only a few days at 2 degrees centigrade. And we used to say that it may reach 30 degrees north on the coast of Florida. But now maybe we have to change that. It seems to be expanding. Now, we've always seen, whenever there's been a decade or so of warm winters in the northern Gulf Coast and on the Florida coast, Atlantic coast, we find better growth of the mangroves at this northern limit of their range, and maybe a bit of expansion, but then there'll be a bad winter that cuts them back. Colleagues down in those regions seem to be taking the existence of mangroves at this edge of the range quite seriously, and there are a number of projects monitoring mangrove expansion, such as Merritt Island National Wildlife Refuge, and that's where this photo comes from. And it was given to me, thank you, Lorraine Simpson, by Lorraine Simpson from the Smithsonian Environmental Research Center, which is studying range expansion on the Florida coast. However, to look at blue carbon impacts, we're going to have to go west to the Texas coast, where Bianchi and colleagues have looked at the impact of species range shifts in the very aptly named Mud Island. And here we see from 1951, 67, 2008, the percent vegetation cover change in mangrove, the black bars, and Spartina alterniflora, or salt marsh cordgrass, as it's called in some areas, in the gray bars. So they looked at two different sites, one where mangrove expanded and one where salt marsh, or at least Spartina alterniflora, expanded. And they cored these two sites to look at carbon accumulation rates. And here are the cores from the mangrove site on the left, the carbon site on the salt marsh site on the right. And there's a lot in these, so let me go over them. Here is depth from the surface to 90 centimeters. We can see the deepest samples were just a bit below 80 centimeters in the mangrove site. The axes are the same on both. The dotted line, horizontal dotted line, represents 1900, much deeper in the mangrove than in the salt marsh. And Bianchi and colleagues were able to determine this because they dated the sediments with cesium-137 and lead-210, which gets us back at least 100 years. And you'll see on the right-hand axis other years labeled. So they have a nice age model. So the first thing that should strike you is the more rapid accumulation rate in the mangrove-dominated site, which alone might account for more carbon sequestration. But let's look at the carbon pool, and the axis for that is at the bottom, and that's in kilograms carbon per square meter on both. And the carbon is represented by the black squares in both. And what we see is, as the mangroves started to dominate in the last few decades, we see a major increase in the carbon storage in the mangrove site. And what's really nice to see, well, if you care about carbon storage, I guess, is the pool of lignin. And that's the upper axis, 0 to 0.25, and those are the kilograms of lignin per square meter. Again, the axes are labeled the same, and lignin in these open triangles is tracking the carbon. And since lignin is such a refractory form of organic matter, it means that this carbon is also likely to stay in the soil longer. It's going to be resistant to decomposition. So it may mean that increases in the range of mangroves mean increases in carbon sequestration. But we'll go back to the north again. Well, actually, we're going to cover a wide range, because we might have increased decomposition with increases in temperature, but we also may have increases in production, particularly in northern marshes where the growing season is quite limited. Kerwin and colleagues were able to look at material from Couche-Borac National Park here on the coast of New Brunswick in Canada, which is pretty far north, and these marshes stay frozen through April, down to the southern coast of the U.S., North Inlet in South Carolina. And they're looking at decomposition. You see the results in this graph to the bottom with years in different colors, 2008, 2009, 2010, versus soil temperature from 10 degrees C to 30 degrees C. And their proxy for decomposition is percent tensile strength loss per day, 0 to 8 on the vertical axis. So essentially what they did is they had buried strips of a standard cotton cloth into the soil. That cotton is removed from the soil, and then its tensile strength is measured. And the more decomposition of that cotton strip, the greater or the less strength it has. So it's going to break more readily. And so it's a standard material that can be used up and down this coastline. So yes, they found a significant increase in decomposition. But then they said, well, what about if we have increased production? So what Kerwin and colleagues did is they cobbled together results from other experiments where either CO2 was elevated that would cause a 3-degree increase in global temperature, and that's what you see in the dark green here, or what I'm more interested in is where Spartina productivity is increased due to 3 degrees warming. The two light green bars represent Spartina altiniflora increase, and this represents percent increase in productivity or decomposition from 0 to 50 in the vertical. And what's really interesting is that this third light green bar represents Spartina patent shoots. And that's interesting for us in the north because most of the marshes we have really are vegetated by these flat platforms of Spartina patents. So Kerwin and colleagues calculated how much decomposition would occur with 3 degrees warming and compared that increase to production and came up with the tempered conclusion that while decomposition has lower sensitivity to climate change, to global warming, than production. So maybe marshes will even become more efficient carbon sinks, at least in the north, under climate change. But certainly they should be maintaining their resilience to sea level rise in terms of the importance of carbon stocks anyway. So, okay, let's move on to storm intensity. Global climate models don't predict more storms, but they do predict more intense storms, making marsh and mangroves all the more important, but actually threatening mangroves and their ability to serve as active carbon sinks. In 1998, Hurricane Mitch passed over the Honduras coast, toppling mangroves. Now, when it hit, depending upon the time it made landfall and the direction of the winds at that time, meant that there were different levels of impacts, particularly on the islands off the coast of Honduras. Cahoon and others took advantage of the varying levels of impacts to use this as an experiment to see how loss of mangroves would affect the marsh or the swamp soil elevation. So what you see is toppled mangroves to the photo, and this graph shows the results from the basin mangrove forest. They also looked at fringe, but this is more dramatic. And they measured elevation with something called an SET. Here we see elevation change, 0 change to +20 to -20 in millimeters. The open triangles represent the high impact site, where after 15 months, still no live mangroves were encountered. Nothing. The site seemed to be devastated. The open circles represent the low impact site, solid the medium. So let's look at the change from May 2000 to August 2001. Each of these represents another event in which they were sampling elevation. There are seasonal differences in elevation due to water in the soil and in places where there's something growing the soil growth. Now, although there was some material depositing on the surface of the high impact site, it still showed a major elevation decrease. Why? Well, if we lose the mangroves, the roots in the soil also die. And when the roots die, the roots collapse, which means loss of volume contributed by the roots, which means then the elevation decreases. And in situations with rising sea level, it could mean loss of the system, because there might be a moment at which that site is saturated for so long, is covered by water so long that mangroves cannot recolonize, which means loss of the active carbon sink. So in such sites, will recovery be possible without assistance? Maybe not. Because of rising sea level. So this sea level rise sort of broaches mitigation in my topics. I had a difficult time where to put it. Even if we stopped all CO2 emissions today, sea level would still continue to rise because there's a lag in it. Ben Horton and others cobbled together estimates from experts as to what sea level rise would be up to 2100. That seems to be the standard target, even with the IPCC's RCP 2.6, which is the most positive future and one no one expects to see. There's still going to be a sea level rise. But what we see is there are various estimates, but it's going to increase no matter what. And what will happen to that? We're likely to get coastal squeeze in marshes and mangroves, particularly in urban areas. So let's jump to the second point. With accelerated rates of sea level rise, the vegetation at the seaward edge, which is a lower elevation, may be submerged too long, and it will die because they can withstand submergence, but still need to have a period in which the water's drained. So these plants are unlikely to persist, and they'll no longer be an active carbon sink at the lowest seaward edge. The fate of that carbon, well, some geologic record shows us that some will be preserved, but we don't know how much. So let's jump up to the upper point. The geologic record also shows us that as sea starts to flood terrestrial systems, well, it kills off the plants growing there, but then allows marshes and mangroves to colonize the terrestrial lands. So marshes can migrate inland. So if we had no barriers to the migration, we might continue to have the same area of active carbon sink. But picture the shorelines in most developed coastlines. We have hotels, we have sea level, we have seawalls, we have all kinds of barriers to that inland migration that will prevent expansion. So we're going to have a squeeze of that habitat, not just the loss of the active carbon sink, but the other ecosystem services as well. We have mapped this out on a continental scale to find where the sites where the greatest coastal squeeze would be, and you see those in red in these expanded bits here. But you know, as my colleagues and I thought about this, we thought, well, maybe it's too late for the areas that are facing the greatest coastal squeeze. Maybe we should be looking at the areas that face the moderate level of threat, because those are the places we can perhaps buy up land and buffers, such as this mangrove site was ranked as high impact, and this is mangrove in a very urbanized part of Mexico. But you can see some open areas that could be maintained to help provide it with a place to migrate. So let's get to, okay, so we can mitigate as we adapt. And one way to mitigate the impact of coastal squeeze is to look at something called the Coastal Squeeze Index. Dante Torrio, who finished his PhD recently in my lab, developed an index, and he applied it to a number of marshes, including the National Estuarine Research Reserve at Wells, Maine. And here you see where future sea levels will be. And he was able to reduce this to an index, both to look at different areas around a marsh to determine where there's most likely to be a squeeze. So either where do you give up, or where do you take very big action, great action, or we can also compare multiple marshes. And that's to determine where we have the best chance, or where we need to take action, or maybe where we should not be supporting restoration. Okay, so on coastlines, adaptation to sea level rise also means mitigation, and I don't have much time to cover living shorelines and hybrid shorelines, which is a great way to both increase carbon storage and adapt to sea level rise. But you could go to this publication by Ariana Sutton-Greer and colleagues in 2015 in Environmental Science and Policy, and they have these great diagrams and descriptions of different ways the public and managers can start looking at both adapting to sea level rise and storing carbon. Restoration of lost wetlands is another way to adapt to sea level rise, particularly in places where marshes were reclaimed for agriculture. There are expansive areas in Canada and in Europe, and particularly the UK. And now there is a way to fund that by putting the carbon that can be stored through restoration on the carbon market. There was already one for restoration of Mississippi Delta wetlands in Louisiana, and very recently there has been a methodology approved. There is now a verified carbon standard, and here is the URL for it, for restoration of seagrasses and tidal wetlands, so salt marshes and mangroves. However, my last warning or caveat is if we should be using mitigation to achieve no net loss. In Canada and the US, there are programs, no net loss of wetlands, and these supposedly can be achieved by giving up an existing wetland and creating one or restoring one in another location. Now, the formulas to figure how much new wetland should be created consider biodiversity, but I don't think any of them consider carbon loss. Let's go back to the marsh at Wells, Maine. And the student in my lab, Lee Van Arden, has recently produced these maps showing the thickness of the carbon-rich deposit, the blue carbon deposit. The deeper the color, the deeper the deposit, and you can see here at Wells it gets up to 4.5 meters. If we just pave this over and had a new carbon sink created, maybe we would maintain it. But anything that causes loss of the existing carbon stock should be considered in any mitigation formula. And here we have thousands of years of carbon. So even if we replaced the marsh with something a new system that was accumulating carbon at the same rate as the old system, we still haven't accounted for the lost stock. Now here is an example of where some of the great potential is, but we don't know how much carbon is going to be stored over the longer term because these actions are still pretty new. Here is managed, not retreat, because the British do not retreat, so they changed the term to managed realignment. And we see an old dike or wall, seawall, that was moved back. And now you see the system that's reflooded. And they get pretty muddy at first in these sites. But if we go to All Fleets Marsh in Essex, where a consulting firm has looked at the rates of blue carbon burial over the first 7 years, and they see these really dramatic numbers, grams of carbon per meter square per year, over the global average for salt marshes. Now, not until this morning did I get feedback from them about this, because these seem outrageous. And what somebody just told me this morning by email is that there is algae that starts to grow in here, and it gets buried. So maybe this is a very positive thing. And the All Fleets Marsh actually has been valued at about, I think, 7 million British pounds in terms of the value of the new carbon stored. But that's just 7 years. We don't know what happens over the long term. We can turn to work of Kraft and others who looked at rates of carbon storage in created marshes. Now, these are marshes where sediment was placed and then Spartina alterniflora planted on the North Carolina coast of the U.S. Here is the organic carbon in grams per square meter per year that's accumulated. And this represents not a single marsh over time, but marshes of various ages that were created almost 30 years ago to one that's only a year or two. It does not show us the same amount of carbon storage as in the managed realignment, and it does not show any nice increase over time either. So this is a caveat in terms of created marshes, and it'll be interesting to see what we can measure in these big sites where we're restoring the reclaimed marshes. And I hopefully end with that caveat for anybody who gets involved in wetland mitigation to please look at the carbon stocks as well as the biodiversity. With that, I will thank you, and acknowledge all my students. You see some of them here, and all the different granting agencies, including Cushawack National Park and Wales National Estuarine Research Reserve, who have allowed me to poke holes all over the place and have had faith, and they still exist, and they're great carbon stocks.
All right. Thank you, Gail, for that presentation. There's a lot of good information in a short amount of time, so that's good to have all those examples from all over. If you're ready, let's open the question-answer period of our session. I see a couple people have raised hands. Again, if you'd like to ask a question, you can either type it in the questions box, or I can read the questions in the order they submitted. I'll try to unmute a couple of the people that have asked questions. They're wrong. Bill M., are you unmuted? Bill Morgante. No? All right. Let's try Ed R. Or are you still muted? All right, let me see. I got a question typed here. Can you please expound on the potential use of the coastal squeeze index for use in prioritizing not allowing restoration?
To put carbon on the carbon market from any activity, particularly, well, wetlands, is we have to show that it has a potential for 100 years. And there are a number of marshes in New England and mangroves in Mexico, in fact, that have already been ranked by government or quasi-government groups as targeted for restoration. But no one has bothered right so far to look at whether these systems will still exist in 100 years, or certainly have the area that they have. So if we can look at the coastal squeeze, and we can do this because we can see very easily see where the inland boundary of the wetland is now, and with remote sensing, measure the slopes and measure the something called impervious surfaces. If you've ever worked with remote sensing, impervious surfaces is a good indication of where there is development. And so we can measure the degree of imperviousness around the system, and knowing what the future sea level is going to be in the area, actually come up with a level of threat to those systems. So we could rank marshes or sites identified for potential restoration. I hope that helped a bit. If anybody, I don't think I put my email address up here, but I'm more than happy to send people reprints of some of these studies that we've done, including the coastal squeeze one.
Okay. Also, let me see. You mentioned earlier this big difference between freshwater wetlands producing methane and the mangrove or the salt marshes that produce less or don't produce as much. Can you expand a little bit on that difference?
Okay, the reason that salinity is a good predictor of methane emissions from marshes and mangroves is that the microbes that would be producing methane in the soil are busy. Instead of reducing carbon dioxide and methane, they're reducing sulfate to sulfide. And the greater the salinity, the more sulfate, because the more seawater influence there is. And so I can't quite get a straight answer because I don't think the microbiologists have sorted out. So it's either the same microbes are busy reducing sulfate from seawater, or the microbes that do reduce sulfate from seawater compete with the microbes that would be producing methane from CO2. And these tidal systems get flooded and drained, many of them twice a day. And when methane is produced and moves through the oxic layer of the soil, it can be oxidized, so that even if it's produced at depth, it may not make it out of the surface soil. What's interesting is some studies of mangroves have monitored methane, and they've shown that the pneumatophores of mangroves can shunt methane from lower layers out into the atmosphere. The number of pneumatophores was significantly actually related to the amount of methane measured in the gas chambers placed over the mangrove soils. So they can, depending upon the kind of vegetation and the salinity. But generally, we can't really measure much methane at all coming from most of these systems.
All right, we had a question about, can you give your email address? I'm assuming that if people Google you, they could probably find your email address.
Yeah, they probably could. Unless I can advance slides, but I can't type on them from my location. My email address is my name, gail.schmura@mcgill.ca. So it's pretty simple.
Okay, thank you for that. I'm looking for more questions, but I don't see any right now, and we're probably going to have to wrap up in a couple minutes.
Yeah, because we've used up most of the time, I think.
So I will, let me see if I can get the slide to go back. First of all, I'll say thank you to you again, and I'll promote the upcoming late May, early June Society for Wetland Sciences meeting in Corpus Christi, Texas. So if you're interested in going to that, sign up to go. There should be a pretty good diversity of talks and issues presented. We can make new connections and catch up with some of the past friends and maybe get involved in some of the other activities that SWS has available to the folks attending. And with that, and otherwise, we'll have another webinar. You should watch your emails for the next webinar in mid-May, I believe, just before the Corpus Christi event. So with that, I think we'll wrap up.
Okay, thank you.
Well, thank you.
Thank you, everybody who stuck out the webinar. I realize everybody has very busy days.
Okay, thank you, everybody. Bye.
And thanks, Tony.